and Mark Twain, and you're very welcome to have your coffee break there. Just don't go to engineering, okay? Go to Hill House and enjoy the view. And coffee and cookies, okay? Cookies is the most important. All right. Okay, so now it's my pleasure to announce our first speaker this morning, who's Gus Schrader from Northwestern. And he's going to tell us about the types of the data.
Yeah, thanks, Vanya. So yeah, first of all, I want to really express my very great thanks to the organizers for organizing this event under such trying conditions and for inviting me to speak. Because it really is a tremendous honor to speak at this event for such a 60th birthday. As I think will be clear from the talk, Sasha's work and his ideas and his enthusiasm and generosity in sharing them has really informed to a huge degree the way I think about that. So it really feels great to be able to speak here. Okay, so I want to begin with some kind of background and context for what I'm going to talk about. And so let's, oh, and by the way, is the volume okay? Everybody hear me more or less? Good. Okay. So let's let S be a topological surface. So possibly having some boundary. And let's fix a reductive group G. So then the classical character variety associated to this pair, let's call it log TS. So this is well, it's the quotient of the affine variety of all representations of the fundamental group of our surface S into the group T. Let me take the quotient as an affine variety. We take the quotient as an affine variety by the natural conjugation action of T on the set of such representations. Affine variety. And in fact, the ring of regular functions on that affine variety comes with a Poisson bracket. So let's say Poisson variety. The Poisson bracket is this famous Atiyah-Bott Goldman bracket. Okay. And a sort of fundamental and at this point very well studied problem is to construct a quantization of the Poisson algebra of regular functions on the character. So a deformation of this to some non-commutative algebra, such that we recover the Poisson bracket on the special fiber when it becomes commutative. Okay, so this is a basic problem, and in fact, this is not the entirety of the basic problem because this character variety, it comes with an action of the mapping class group of the surface by Poisson automorphisms, and we like to in fact construct a quantization which is equivariant with respect to the mapping class group X. Okay, so as I said, this is a very kind of fundamental problem. And there have been lots of different approaches to it. So some sort of particularly influential ones, I guess, were work of Fock and Rosley and Alexeyev, Grosser, Shermeris, using kind of combinatorial quantization involving graph connections on the surface. and also kind of approaches via skein theory, so pioneered by Turayev and collaborators, and many others as well. But at least from my perspective, a really big kind of innovation in the subject came from the following idea of Sasha and Volodya Park. So let me maybe just draw one more thing on this diagram. So let's suppose that our surfaces now can come with a collection of special points. And some of these special points could be on the boundary of the surface. And let's also, on the group theory side, we'll also split things up a little bit. So let B be a Borel subgroup inside of our reductive group Q. And so then we can consider another modular space. Let's call this XGS, where if we think about our G local system as a principal G bundle with a parallel transport, then at each of the special points, special red points, we equip our local system with the additional data of a reduction to a Borel subgroup. And in this way, we get some modular space, XTS. And we have an obvious forgetful map down to our classical variety where we just forget this extra data of the Borel reductions. Okay, so it may look like doing this has made our life more complicated, but in fact, it, in a certain sense, has made it much simpler. Because in contrast to this quite complicated affine variety log TS, this variety XGS is in fact a rational variety. In fact, even better, it's called a cluster Poisson, meaning that as Bridges explained this yesterday, that it comes with an atlas of Poisson tori with combinatorially defined subtraction-free Boolean maps. And then there's a beautiful general theory of the quantization of these cluster Poisson varieties due to Sasha and Volodya again. And we can feed this cluster Poisson variety XTS into that machine, and the output is precisely a gamma S equivariant quantization.
Of XGS.
Of XGS, precisely. In the case that the surface only has special points in the interior, then this map over the generic point is just a Galois covering with Galois group, the WOW group of G to the number of special interior points. And so we can recover the quantization of this just by taking the variance for that WOW group action. Okay. Right. So the next kind of piece of background that I want to mention is another idea first appearing in the work of Sasha and Volodya, and then sort of fully developed in his later joint work with Shen, is that this cluster Poisson structure can be understood as being glued from those for simpler surfaces. So think of what is the simplest kind of surface we might want to glue this cluster Poisson structure from. Well, maybe the simplest of all possible surfaces, we should make a disk. Okay, but unfortunately, from the point of view of studying G local systems on a disk, at least as a set or as an affine variety, that's not a very interesting space. It's a point. So we need to do something a little bit different. And what we can do is we can add in 3 special points on the boundary of this disk. And now, in fact, we can, to make a sort of a triangle, and in fact, we can, in fact, glue what's my spaces. these, with one small additional caveat, that at marks on the boundary, like the ones we have here, we should consider a reduction to the unipotent radical of our Borel rather than Borel itself. In other words, we should consider local systems with dependence. Okay. So this is sort of a brief recap of some of the innovations in the subject in which Sasha had a decisive part. And the work I want to talk about today is very much inspired by this idea of understanding these localized spaces and their quantizations by gluing them together from simple pieces. And one of the messages that I want to convey in the talk is that if one really wants to understand gluing from the simplest possible pieces, then one is more or less forced to work in the context of something like stacks. Right, as you can see from kind of the discussion we just had, right? After all, a local system on a disk, well, there's only a point's worth of those, but that point has interesting automorphisms. Namely, the has an automorphism group given by the whole of Z. So if we want to get a really glue from things like this, we're forced into working with stacks. Another argument in favor of considering something like stacks is that when we add in these B reductions, we leave the world of affine varieties, because now we're dealing with varieties built out of stuff like flag varieties, space of B cosets in G, which, as we all know, are flag varieties that project and they're not out. So when we pass to algebras of global functions, we're losing some information about the modulus. And so perhaps it would be better to work rather than with algebras of functions with something like instead categories of coherent sheets. Okay. So with these sort of apologetics out of the way, I want to kind of explain the goal of the talk. And this goal is to describe I call the quantization decorated character stacks. Let's give these sort of unpronounceable name Sh, G, and S. Okay, so what do I mean by this? Well, I mean that for any so-called decorated surface, bold S, I'll explain what it means in a moment, we're going to construct a category, the role of the category of varieties on this stack. Let's call that Z, U, S, and should also fix G before suppress it in the notation on the right-hand side. And so we'd like to construct a category like this. And we'd like this construction to be functorial and strongly local with respect to the decorated surface S. Okay? So the functoriality is immediately of this construction will immediately guarantee mapping class groups equivariance. And this strong locality will lead us to this, what I think is the second message of the talk, which is that the whole structure of the quantization of these moduli spaces is in a precise sense governed by the representation theory of quantum groups. So that's what I hope to explain. Yes.
So should I think the category as category of modules over quantization?
No, you should not, because these are not affine stacks, not affine varieties. So it won't be equivalent to the category of modules over an algebra.
No, but I can think about category of.
Oh, yes, yes, absolutely. Yeah. Right. Precisely. Yeah. Mm-hmm. Yeah. Good. Yeah. I'll explain it in a moment. Good. More questions before? Okay. So at this point, I want to, I think, get a theorem on the board, and I'll spend the rest of the talk explaining what the theorem, all the things in the theorem mean, and the rough ideas involved in its proof. So this is a theorem we proved in joint work with David Jordan, Ian Lee, and Sasha Shapiro. And now sort of brace yourself for a torrent of gobbledygook, which will be explained. So for any one of these decorated surfaces S, we construct a category ZQ of S as the factorization homology of S, the stratified factorization homology of S, which I'll denote by this integral over S, of what? Of what I'll call the parabolic induction algebra associated to the quantum Borel subalgebra in the quantized universal enveloping algebra associated to our group G, together with the corresponding quantum universal carton. So in other words, here is the modulo. This map is the projection. This one. Okay. Again, don't worry for now what it means. I'll explain it in details later. But the point to take away now is that this defines as some category associated to the set of S. Okay. Now, when a decorated surface S is simple, again, I'll explain what it means, but what you should think is that it corresponds to one of these surfaces considered by Sasha and Bologna, where we allow some special points in the interior and some on the boundary, and not some more exotic thing. So this is an important restriction. The next one is a restriction due to our own limitations, hopefully temporary ones. And that restriction is we're going to demand our group have semi-simple rank 1. So it'll be either SL2 or PGL2. So in this case, for each ideal triangulation, of our decorated surface, there's a canonically defined open subcategory inside of the categories associated with the surface. And this open subcategory really is, in the strongest sense possible, equivalent to the category of modules over an algebra. So it's equivalent to modules over some quantum torus. Call it phi delta. And that quantum torus carries an action of a group built from the carton subalgebra of the quantum enveloping algebra. And we consider the category of modules that are equivariant with respect to that action. We only write that as torus subgroup. Right. So this thing's something like a chart on a piece of this stack. And, yeah.
An open subset. Right, and the category of fifths of an open subset is a proof.
Yeah, good. So you can think of the quotient is, so what does it mean to be an open subcategory? It means that your inclusion has an exact left adjoint. And so you can either think about it's like a linear algebra, think about the kernel of the matrix, or yeah, the orthogonal complement of the matrix or the kernel of the transpose matrix. Mm-hmm. Other questions? Yeah, good. So, right, and so then when we have two ideal triangulations related by a flip, then the canonical comparison functor, transition functor rather, functors between these two open subcategories are given by mutations of quantum torque. So in the case that our group is essential to, we really can, in quite a strong sense, compare the categories we construct this way with the cluster quantization of Bock, Gaucho. So when I explain the rest of the book, explaining the meaning of all of this business. Okay. So the first order of business is probably to explain what is meant by a decorated surface.
Because after you wrote this formula, you already defined what's
Exactly, yeah. No, that's it. But we'd like to compare it with your construction. Yeah. Precisely. So once we write RecQ, as we'll see, everything is defined, but in a way that's very abstract and a priori somewhat hard to say much of anything about. So the real content of what we do in a sense is to bring this very abstract fellow back down to earth in such a way that it can be compared with more concrete models for quantization. Okay, so decorated surfaces. So these guys that I've been using boldface S for, so what are they? Well, they consist of the following data. So we have an underlying surface S together with, let me now maybe use some colors, with C, a collection of embedded curves, all of whose endpoints we want to lie on the boundaries below the surface. And so almost most importantly, in addition to this, labeling by G or T of each component of the complement of this union of curves in our surface S. Okay, so let me draw some examples of these things. Let me first tell you how one draws a triangle in this decorated world. So to draw a triangle, we draw a big disk, and we take as our collection of embedded curves 3 little bites out of the disk, like this. Okay, and then we label. So now there are 4 components of the complement of those red curves. We label the bulk one by G, and we label the little bytes, the interior of those little bytes. Let's label that by T.
If I want to label it by G, I don't need to draw a curve.
Well, good. Yeah, if you want to label it by G, you do not need to draw a curve. Exactly. Yeah. Precise. Yeah, you could label it by G, but then there'd simply be no, as you see in the moduli problem, there'll be no additional data. Good. So this would be a triangle. Let's do one more example. So let's now take an annulus and as our see a single red loop in the annulus. And let's color one of these regions by T, these 2 components by T, and the other one by G. So these are the kind of things one might consider. And now I can explain what I mean by simple, which is simple. The stipulation simple means that all of these T regions retract onto the boundary of our surface. So here they retract onto small intervals on the boundary, and here it retracts onto either of the boundary components. Okay, good. So, oh wow, mic turn on. Okay, so that's decorated surfaces. We now discuss decorated local systems. So a decorated local system is really a triple of things: EG, ET, and EV, where EG and ET, these are respectively G and T local systems on the part of the surface labeled by G or T, respectively. And what is EB? Well, on the set of curve C, we have a G cross T local system, just given by the product of EG with ET. And EB is a B reduction of that G cross T local system along the product map from B, where we have the product of the inclusion to G and the projection to T. Okay. And yeah, and the main object of study for us is this moduli stack GS of decorated local systems on a decorated surface. So how to think about this stack, or if you like, the category of sheaves on this stack in some concrete terms? Well, we can do the following fairly standard trick, which is that we can add some additional data, which is in our paper we call these gates. It's a funny word for something very, very simple, but it's just a collection of intervals on the boundary of the surface. And if we do that, we can consider a kind of framed version about a moduli problem, where on each of these intervals, we equip ourselves with the extra data of a trivialization of the corresponding local system. At each one of these gates. Okay. And in doing so, a trivialization of, right, so these intervals lie, or some intervals contained inside one of these T or one of these G regions, boundaries of one of these T regions. So it's a trivialization of EG or ET, depending on where the interval is. So this fellow is actually a variety, and it gives us a presentation of our original stack as a closed system. Provided, of course, we add a gate, at least one gate for each component of the complement of these systems. We have RG components and sort of ST components. We'll get it. Okay, so let's come to these examples and understand what these modular spaces are concretely. Okay. So again, as we said, that the way to do this is to add in these gates. Let me draw them as some little sort of blue. Whoops. That's not what I wanted to draw at all. Well, I can keep one of these guys. So remember, I only need one gate on each component of the boundary. So I'll put one gate in this G region and then gates in. Okay, so now I've trivialized everything. And having done that, well, we have a disk, so the underlying local system is trivial. All that's left is the data of these reductions, which amount to B cosets, the choice of a B coset in G cross T. And we have 3 of those guys, and that is our fully framed variety. So, of course, another way to say what are B cosets in G plus T, that's the same as N cosets in G, right? Because G cross T acts in the obvious way on G mod N, T from the left and T from the right, because it normalizes N. And the stabilizer of the identity coset is clearly the subgroup B. So this is the product of 3 copies of this principal flag variety G mod N. And now we can forget the much too small. We can forget our G gate and get a map to this configuration stack of 3 points in G mod N. And then if we like, we could further forget the T gates and map to what right it is. G mod B cubed mod from the right by T to get T mod B. So that's how things work in the triangle. Let's do one more for this annulus. So what's the story here? Well, again, we frame everything. Having done so, now the data that we have is we have 2 local systems, a G local system and a T local system. Having trivialized, those are represented by an element of G and an element of T, the 2 holonomies around the obvious loop. And now, again, we have an element F in this principal flag variety, which, so for this to be a reduction, it needs to be preserved by the holonomy of the G cross T local system. In other words, we must have G F T inverse is equal to F. Okay. Now, of course, because this principal flag variety is just a T torsor over the actual flag variety, we can re-express this by just forgetting about the T holonomy, just remember the G holonomy, the principal flag, and now the condition is that G preserves the image of that principal flag under the projection to G mod B. Of course, you can recover back the T by looking at the monodromy of the principal flag under because it's just the T torso. So this is just the same. And now we can go ahead and forget the wolf like the T gate. And forgetting the T gate identifies this with now just elements G in G and flag in G mod B such that G preserves that flag. In other words, this is the Grothendieck multiplicative Grothendieck Springer resolution. Okay, so hopefully these examples are a convincing argument that this setting of decorated surfaces is a very natural place to be doing a kind of geometric representation theory, at least in a multiplicative kind of setting. Okay. Good, so I should probably keep moving. You can also do, if one wants to make the Steinberg stack, one could of course take the fiber product of two copies of this guy over a G annulus. In other words, add in a sort of another little T halo around. Anyway, so all of these kind of varieties stacks can be very naturally understood in this setting. All right. So, so as I mentioned, the kind of key technical tool that we'll use, kind of big machinery, if you like, is the theory of stratified factorization homology. As developed by Ayala, Francis, and Tanaka. I think this is what's now referred to as the alpha version of the theory. There's apparently there is a beta version of the theory, which is some super version, but for us, we'll stick with the alpha one. So what is the basic setup here? So let's consider a two category of decorated surfaces whose objects are, well, decorated surfaces. Whose one morphisms are decorated embeddings, i.e. embeddings preserving the labeling of regions by G, B, or T, and whose two morphisms are isotopies of such. Okay. So inside of this two category, we can consider the full. Oh, yeah, and I should say that this two category comes with a symmetric monoidal structure given by disjoint union of surfaces. Okay, so it's a symmetric monoidal two category, 2, 1 category. Okay, so inside of here, we can consider the full subcategory generated under these disjoint unions by, let's call this subcategory D, the disk. And it's going to be generated by the following three basic disks. So two of these guys, we'll call them D, G, and DT, are disks that are just entirely labeled by G or by T respectively. And then the interesting one, which we'll call DB, is the one involving this domain wall, where we have a kind of bipartite disk, one half labeled by G, the other by T. Okay.
When you say change,
are generated under the smallest monoidal subcategory containing these objects. The objects are just disjoint unions of finite numbers of these three disks. Good. So here comes well, in my mind, somewhat painful part, but also very beautiful part, which is that. So we're interested. Okay. So what I mentioned before that we want to take stratified factorization homology of our surface with coefficients in this monstrosity on the right-hand wall. So now I want to talk about what are coefficients for stratified factorization homology. So these coefficients are what you might call disk algebras. What do I mean by that? I mean symmetric monoidal functors from this disk category. Let's call this functor F to the two category of k-linear categories. The usual thing we functors as one morphism, natural transformations as two. Okay, so such functors are going to be what serve as coefficients for our factorization homology. And once we have such a thing, well, remember that this disk category includes into this two category of decorated surfaces. And we can take the left Kahn extension along that inclusion, which defines this uniquely, if somewhat abstractly, a functor Z from this two category of decorated surfaces to the two category of k-linear categories. And so this thing is the stratified factorization homology as defined by Ayala Francis Tanaka. So again, this is extremely abstract, but the goal of the talk is to explain how one can really boil it down to something very concrete and almost combinatorial. Okay, but first I want to discuss the kind of structures, or to really discuss in more detail what is one of these coefficient systems. Okay, so what is one of these disk algebras? Well, let's think about the kind of structure that should be assigned to the categories associated to the G and the T disks. Okay, so by including one of these disks inside of a third one, we see that this category should have some monoidal structure. And by considering the isotopy of embedding, where we braid these two guys about one another, we see that it should be a braided hence the category that we assign to a G or a T disk. What about a B disk? Well, again, we should have a monoidal category, because again, we can include two smaller B disks into a third B disk, but notice that now there's no natural notion of braiding. You can't braid these two guys around. So again, we have some monoidal category. But notice we do have some additional structures, right? Because we can include a small G disk in here, or a small T disk in here. So this F of dB should be the recipient of a monoidal functor from the product of our categories assigned to the G disk and the T disk. And what's more, because I can factor the inclusion of a G disk through an inclusion of a B disk in the following two ways, which give me literally the same picture once I forget how I factored. Right, so I have these two factorizations given by the orange and the blue things that I just drew, B disks that I just drew. And so this functor should come with a half braiding. I'll explain in formulas in a second exactly how that plays out. Okay, and so the source of categories bearing all of these structures for us is going to be the representation theory of quantum groups. So as our braided tensor categories, we're going to take the categories rep QG and rep QT, with the braidings coming from the universal R matrix.
Does this put any restrictions on?
Good. So here, for what's being said here, okay, if you want this to come from a universal R matrix, then you probably should be careful about how you treat roots of unity. But in any setting where you can define a sensible braiding, the following will make sense. Good. Okay. So we have these two braided tensor categories. How about our monoidal category? This will be representations of the quantum Borel subalgebra. Okay, and now what is this half braiding? Well, imagine if I have some V, a representation of UQ of G, and M, a representation of UQ of B. Well, then by the half braiding, if we form the tensor product by I star, I mean restrict V to a representation of B, tensor it with the representation M, then I claim the universal R matrix, the G, still makes sense here. And then flip, I guess, to give us a morphism of in rep QB to M tensor S star of V. The reason for this is, of course, that by the construction of UQG as the Drinfeld double of UQB, this fellow here lives inside of UQ of the opposite Borel, tensored UQ of the Borel. So its action on here makes perfect sense because UQB knows that we will act on a B modulus. So this is the source of our system of coefficients for the stratified factorization. Okay. Good. So now at least we have some feeling for the definition of most of the things on the right-hand board. And in the remaining 12 or so minutes, I want to explain how to actually compute them.
Just to summarize, right?
Yeah. What it is? Yeah, good. So it's this structure here. The structure of these three categories, two braided tensor categories, a monoidal category with a central functor from the braided tensor category. So functor to the Drinfeld center of this is a fancy way to say this thing I said about the half braidings. Yeah.
This is just torus, right?
Yeah, that's right. It's just the torus with the braiding given by the Cartan pairing. So if you have a vector of weight lambda, a vector of weight mu, you braid by swapping and multiplying by this power of q. Yeah. So yeah, the actual algebra is commutative, but the braiding is good. Okay, so how do we compute anything based on this very abstract looking definition, can't extending along an conclusion? So the real key to it is the fact that stratified factorization homology, as proved by Ayala Franciscanica, satisfies what's called tensor excision. So let me explain what this means because of the situation of time by way of an example. So let's imagine we have some surface. Let it be, for us, a two-gon diagonal. So we have G in here and T in here. And let's suppose, so here's our D, let's call it D2. And let's suppose that we can write our surface as a gluing of two surfaces, which in this case will be two copies of the B disk glued over a kind of cylindrical surface. So a surface is the product of some one manifold with an interval. In this case, it's this fellow here, and the interval goes in this direction. So we're gluing over that thing we're gluing over topologically is just a G-disk. Okay, so then in this situation, that the category associated to this cylindrical surface, that's a monoidal category, as you can see from the functoriality and the fact that we can kind of stack together these cylindrical guys along the interval direction. Right? So this guy is monoidal. And by the same argument of stacking along the interval direction, we see that this monoidal category acts on the categories associated to the two surfaces we're trying to glue together, right? You think about including this thing here into this thing here, that when you apply the functor will give you an action. Okay, and so what excision says is that the category assigned to the whole surface that we're trying to glue up is equivalent to the relative tensor product of the two module categories associated to the two pieces, which in this case is just two B disks, over this monoidal category over which we glue. Okay, so in this case, it's the relative tensor product of two copies of rep QB over rep QG. Yes, thank you. It absolutely should. Good. Okay, and this is completely general. For gluing any two surfaces over any cylindrical surface. Okay, so this is the first really key tool. But in order for it to be useful, we need to have a concrete understanding of rep QB as a module category for rep QG. Otherwise, we have no hope to go any further in terms of our description. And that's the second really key ingredient, and really a big one of the things we prove in the paper. So how to understand rep QB as a module for rep QG. Okay, so I think I do want to spend time explaining this, even at the cost of perhaps missing out some details at the end, because I think it's really the crux somehow of the issue. So, and I want to develop some intuition for what I'm going to say by thinking first about the classical case. Okay, so classically, the classical version of what we want to do here is something very familiar from classical representation theory, which is what you might call geometric induction. So if we have a representation, let it be M of the Borel subgroup inside of G, then we can form a G equivariant vector bundle on the flag variety by taking the quotient of G cross M by the diagonal action of B. Okay, so this is a vector bundle, G equivariant one, on the flag variety. So we get, like we can write it like this, a functor to the category of G equivariant sheaves on G mod B. Usually. Okay, we could, if you like, think about this, of course, as the category of sheaves on, well, T, G cross T, equivariant sheaves on the principal affine space. And this is looking kind of quite promising because this G mod N is rather close to being an affine variety. On the other hand, as we know, it's definitely not an affine variety. It's like the first example one teaches of when G is SL2, right? G mod N C2 with the origin. First example, quasi affine but not affine thing. So it's not affine. So we can't hope to on the nose identify this category with the category of equivariant modules over an algebra. But of course, again, thinking about basic algebraic geometry, we sort of know what we should do, right? Which is, so in this case, geometry is obviously P1. And we can embed the category of shoes on P1 into the category of modules over the affinization. Let it be O of C2. And the way it gets embedded, you can think about it as the orthogonal complement, as the right orthogonal complement to sheaves supported at or sheaves supported on the complement of P mod n inside of this affinization. Okay, and so in the quantum case, a very similar, we have a very similar kind of picture. So.
Sorry, can you explain that remark slightly further? If I think the delta sheaf at some random point, it is right orthogonal to it's just like the sheaf supported at 0, but it doesn't seem to be a quasi-coherent sheaf on P1.
Oh, so here I haven't imposed, yeah, I haven't put any equivariance here, but you could also, if you like, put G cross T everywhere here, right? And then the only such torsion sheaf you could possibly do would be, yeah, one supported somewhere on C2, which was not at 0, yeah. Okay, good. So at the quantum level, so there's an algebra object, in fact, a braided commutative algebra, OQ P mod n in rep Q P cross T. And inside of the category of G cross T equivariant modules over this algebra, there's a Serre subcategory of torsion in the appropriate sense. And one of the theorems we prove in this paper is that the category of representations of the quantum Borel is again equivalent to the right orthogonal complement to torsion inside of this category. Okay. And so now this is what really puts us in business. Because now we can compute. Okay, so now we have a description of the category assigned to a single B disk in terms of modules over an algebra. And now we can compute the category assigned to, well, an n-gon, in particular a 2-gon and a 3-gon, so in sort of interval of a triangle by excision. And I want to conclude by explaining how this gives us the open subcategories corresponding to ideal triangulations, or at least gesturing at that before we start. And so the key point, right, is that it all boils down to the story really for, at least the definition of these subcategories, boils down to the understanding the story for G of D2, okay? So by excision, we can identify this thing as the orthogonal complement to torsion inside of, let me now abbreviate this OQ thing by just O. So let this guy just be O. So by excision, the category for the 2-gon is orthogonal to torsion in the category of equivariant modules over the braided tensor square of this algebra OQ G mod n. Okay. So it probably come as no surprise to learn that as an object of rep QG cross T, OQG mod n is just the direct sum over the all dominant weights of G of, well, a copy of the earliest representation of G of that highest weight. So this is the G factor, and a character of T given by minus that weight. Okay, and so by Scher's lemma, the G invariance in this braided tensor square is isomorphic to the, if you like, the monoid algebra of this cone of dominant weights. Okay, just because it's exactly up to scale of one hom between the two. No homs if we have different weights, exactly one if we have the same. Okay, and so we can consider an open subcategory. Let's call it O braided squared adjoin lambda modules. So this is an open subcategory inside of the category assigned to a two-gon, on which all of the fundamental weights act invertibly. And so we join the inverses of all these fundamental weights. Look at the modules in which they act by something invertible. And the key point is that on this open subcategory, the functor of taking G invariance is actually conservative. Classically, it corresponds to the fact that once you get rid of this divisor, the action of G on configurations of two affine flags is actually free. So this is equivalent to the category of modules over the invariance. This is taking G invariance. And by what we said, this is equivalent to the category of modules over this torus. Now we lose the G action to take invariance, equivariant with respect to the action of T squared. Okay, so this guy really is category of modules over a torus. Okay, and then to finish, yeah, very last thing is that the categories for yes, so in a similar way, we have a category for a triangle, where now we have, because we have inclusion of, we can include D2 into D3 in three different ways. Now we have three copies of the weight lattice. And then these open subcategories corresponding to triangulations correspond to gluing triangles, open subcategories for these triangles over open subcategories for these two using excision. So yeah, unfortunately out of time, but thanks very much for your attention and happy birthday, Seth.
Are there questions?
Do I understand correctly that rep QG is just category of finite dimensional representations?
Yeah, good. So integral. So yeah, we need something like integrable representations. If we want to have objects like this OQG mod n, which is like sum over all finite dimensional representations. But yeah, integrable is sort of the right way to think.
So, but then how Rishi-Tikhon-Turaev, I mean, topological field theory, sit inside this construction?
That is a very good question, to which I don't really yet know the answer. So yeah, so for that, one should work with something like this category. So now we have to be careful about which kind of category we use as RepPG and RepPT. And in that case, one should be something like this category of tilting modules. And yeah, to my knowledge, that hasn't yet been fully worked out anywhere. But I agree that it's, I think, a very important thing.
In particular, the root of unity Does it play any role in your?
So it doesn't play a role in our arguments, but a lot of what I said will work in any of these contexts where we can either take, cat-stick and cuneiform, listic form, this category of tilting modules. There's a lot of possibilities, and I think it remains a little bit unexplored. Yeah.
Maybe it's worth mentioning that what Gus was playing is rather 4D TQFT, and resisting derive is a 3D TQFT, but one can really obtain this resisting derive from here probably.
Any more questions? Yeah.
So, but where to put the horse? So the horse is the little disk operand. Is it somehow
So with it,
little disk operand?
little disk operand. Yeah. So this has precisely structure of these G and T categories, right? Sort of E2 algebras. And yeah, I don't know what the name for this operatic term for this kind of story with the domain walls is. I'm sure there is one, but some more learned person than me will probably be able to tell.
Are there any questions from Zoom? You can unmute yourself and ask. Zoom is silent, so maybe I should ask a question. So how would the restrictions on keys SL2 or PGL arise?
Excellent, good. So where it arises is in giving an extremely concrete description of the invariance. So in the case that G is SL2 or PGL2, the group algebra of the weight lattice is just a Laurent polynomial ring in a single variable. Okay. And correspondingly, when we move to a triangle, what we have to do now is to understand G invariance inside OQ G mod n cubed. Now, when G is semi-simple rank 1, that's again easy to understand, but in general, it is much more complicated. And I think this is where a lot of the interesting kind of aspects of the story lie.
Well, would it be fair to say it's somehow difficult to write?
Precisely. So the difficulty lies, and the sort of, I think the beauty of it lies in the fact that the parabolic induction algebra is now a much richer thing. Because we have more parabolics than just the Borel, right? So now we'll have other parabolic induction algebras. Parabolics P, Libby factor L, and the group G. So now it'll be sort of much richer kind of story. So yeah, this all remains to be like that.
Comment on your question. In high rank, you would also like to consider not just just this line interfaces, but when you would allow them to intersect, and then you'd have just one kind of one more piece of the picture, just not the 3 disks, but a little more disks that you'll have to consider in the beginning.
All right. In the interest of time, let's declare that the questions are over, and let's thank Gus again for this. At 11:35. For those of you who haven't picked their folders, haven't registered,